So, good afternoon, and we are still talking about queues. We talked about a queue, a bounded queue. A bounded queue is a queue that is limited in size, that has a maximum capacity. Today we'll be talking about circular queues. Well, before I introduce the circular queues, just reminding you of something. Do you know a carousel? What a carousel is? This is what we call a roundabout or a hurdy-gurdy or merry-go-round. This fun thing that turns around and around and around. Well, this carousel, this idea, exists in computer science in some user interfaces. Here you can have a carousel of images. And these images, you can slide a slider here and they rotate, and the one that is in front of you changes, okay, as these things rotate. And they can, well, here it's blocked by the slider, but you can imagine you have an arrow on one side and the arrow on the other side, and then it can turn forever, like a real merry-go-round, like a carousel. We call it a carousel. This was in 3D. There are other ones like this in 2D, just one line, and it can go to infinity as well. Let's simulate this. Imagine I have, it's like a menu actually. I have images like this, and I can click on this arrow or that arrow, and they can move to the next one. So in this particular case, let's say I have an indicator, a pointer that says who's the current, like A is the current, and if I click here, then it goes to the next, it goes to the next, it goes to the next. I can click here, it goes to the previous, previous, and previous, okay? This is also kind of a carousel. I'll show you in another kind of simulation. Here, for example, I have the current one is in the middle, okay? And instead of the square moving, it's the whole thing that is moving. See here? I go back, go forward, forward, I can go back. You see the A was on the left, and because I moved everything towards the left, the A goes to the right, and it's the B that goes to the right. Okay, I can go on the other way. So it's a carousel that moves on both directions. And because A has been kicked out, well, it goes on the other side, and it's turning around. It's like a carousel. And the idea of the circular queue will have the same kind of behavior, okay, going like this. Okay, let's, well, before we go to the circular queue, I want to show you this Ouroboros, the mythical serpent, or sometimes dragon, and depending upon the culture, that bites or eats its tail. It's actually, it symbolizes this circle of life and death and rebirth, infinite. Well, you think, well, what is this? This is mythical. Actually, it exists. You have some stupid snakes that bite their tails, and they end up dying. They don't resuscitate. There's no infinite cycle of life and death in this case. But anyways, our circular queue will have some kind of similar behavior. It's not biting its tail, but you'll see that the head is actually, like in this snake, the head is chasing the tail. And because the tail is running away, it's actually chasing the head on the other side. And that's what we'll see in our circular queue. But our circular queue, it's a bounded queue, and it's a linear structure. So it has a front and it has a rear, or a head and a tail. Instead of pinning the head at position 0, like we did for the bounded queue, and remember, in the bounded queue, we had the head at position 0, and the rear was moving, okay, left and right, depending upon whether this bounded queue was growing or shrinking. In this particular case, both the head and the tail will be moving. So the front, the head, is not pinned at position 0. It can be at any position later. And if the front is moving, the front is actually moving to the right, and the rear is also moving to the right as I'm adding new elements. When I remove an element, the front would move to the right. When I add an element, the rear will move to the right. But if both of them are moving to the right and the head is chasing the tail, eventually they reach the end of that bounded queue. And what happens is that when they reach the end of it, they will not go beyond. They will go to the position 0. And that's why it looks like circular. The head is chasing the rear is going on the other direction, also chasing the head, and it's like the snake biting its tail. Okay? And how do I go from the end and jump to the beginning? Okay, when I reach here, how does it? So rear, I add another element, the rear is here, and then I add another element, it goes beyond. How does it go to 0? Well, there is an operator that we call modulo, and it exists in math. It's not specific to the language Python, but luckily Python has this operator. We call it modulo in math, or we write it as mod. In Python, it's this percentage sign. It means a modulo. So a modulo n, it's like a divided by n, the integer, what is left. So it's the remainder of the division of a by n. Okay, so a percent n, which is a modulo n, is the remainder of the division of a by n. And because it's the division of a by n, it's either 0, there's nothing left, or the most that can be left is n minus 1. It cannot be n, or more than n, because then I can divide more. So what happens is that a modulo n is always giving me a result that is in this interval 0 to n minus 1. 0 to n minus 1. Well, that's exactly like the size of a list. It goes from 0 to n minus 1. So, like magic, this modulo operation is giving me something that is guaranteed to be in the boundaries, in this range, basically between 0 and n minus 1. And you think, what is this operation? Well, you're using it every single day. Every single day when you look at the clock, for example. Well, the clock, imagine the noon or midnight is a 0. When your clock is going 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 0, 1, 2, 3, 4, 5, 6, 7, 11, 0. It stays always in that interval. You're used to it. Okay, that's modulo 12. It goes from 0 to 12 minus 1, which is 11. Okay, it's a repetition of 0 to 11, 0 to 11, 0 to 11. You also use it in many operations unconsciously. Imagine here's a farmer, he has some chicken, and every morning he counts his eggs and then puts them in boxes, and whatever is left that he can't put in a box, he will have an omelet. And at the end, so, okay, this morning I have 33 eggs. I'll put them in boxes the size of 6. So here are my 33 eggs. And I will put them in boxes of 6 eggs like that. How many will be left? How many eggs will I have in my omelet? Well, it's 33 modulo 6. Well, here's my first 6, my second 6, my third 6, my fourth 6. They all go in boxes. Another 6. Aha! I have left 3. 3, I can't put them in a box. I'll have an omelet. So 33 modulo 6 is 3. Okay? So this is something it's not that complicated, very easy actually, and we will use it. And modulo 6 is something that will always return a number between 0 and 5. So 6 minus 1. Modulo anything is giving me something between 0 and anything minus 1. Okay? So we'll use it, but before we use that, let's talk about, I'll show you how this circular queue works. Here I have a queue. Okay, it's a queue of 5 positions. So it's bounded by 5. And I put D1, D2, D3 in there. I unqueued them. I unqueued D1 first, and then D2 second, and then D3 third. Now I want to unqueue a 4th one. There you go. I'll put it there. If I dq d1, what will happen? Well, I don't want to shift all these if I remove d1. Actually, I will have its empty space. I'll leave it there. That space is there, but I removed d1, I dq'd it, and then returned it. So this is my state after dq'd. And look at what happens now if I unqueue d4. D5, sorry. And so I add it at the position that is available just after d4. If I now dq d2, I'll get this. So I have these two spots that are empty, and where is my queue? Is d3, d4, d5. I have to have something that tells me this is the front. And where's the rear? Well, the rear is actually here. That's the first place that I can put something in. And indeed, if I do nq d6, that's what happens. Okay, so my head is still here, and my queue now is in this position. It's the next one where I can put something. And now if I dq d3, that's what happens. I now unqueue another one. I dq another one. I unqueue another one. So it looks like it's circle, or like I went back to the position I used to be. Okay, I'll simulate it again with another way. You'll see how this effect of circular. That's why we call it circular queue. D1, put D2, D3, D4. Look what is happening. That white is like going around and round, like the merry-go-round. Okay. But to do this, I need two references. A reference to the head. At each time, I need to know where the head is, and a reference to the tail. And that's how we will represent it. So my first here, the D1, D2, D3, is actually represented here. I have my indices 0, 1, 2, 3, 4. I can put 5 elements. It's bounded by 5. Now I'm showing you the circular queue. It's a bounded queue too. It's bounded by 5. Now my head is at position 0. That's the first one that will be served. And my tail is at position 3. That's the position where I will put the next one. So indeed, if I nq something, I'll add d4, it goes to the tail. And the tail has to move. Now the new tail is the position that is empty. Okay. If I dq d1, where do I dq it? At the position indicated by the head. Okay. There is the dq, 1, poop, d1 is gone. Okay. So I remove from the head, then I have to increment my head by 1. Because now it's referencing the position of the next one that will be the first to be served. Now let's unqueue another one. Where will I put it? I'll put it at the tail. Okay, if I unqueue d5, it goes at the tail. And now I put d5, but tail has to be incremented. If I say tail plus 1, whoop, it'll point somewhere else. It has to go position 0. Okay, and that's why it's circular. It's going around. And how do I make it point here? Modulo 5. 5 is the capacity. So we will use this modulo 5. Let's take this state here. I'll move it to the next slide. I'm here. Now I will dq. Who do I dq? The one at the head. So, okay, I'll dq d2. And same thing, head will move forward. Now it's pointing and referencing the next one that will be served. So if I unqueue, where will I unqueue? There's no room here. Well, I unqueue where the tail is. So I will unqueue here. And tail has to move forward. If I dq, d3 is removed. Notice that at this position, had I added another element, what will happen? Tail will be moving forward, it will be equal to head. But when I start in the beginning, my tail is equal to head at position 0. But there is a risk here that tail is equal to head when the whole thing is full. So how do we test that my queue is full, my circular queue is full, or my circular queue is empty? So we would have to leave an empty spot that is never used. We'll sacrifice it. And we will say that when the tail is equal to head, that means my Q is empty, whether it's a 0 or 1 or 2 or whatever, it stops. Okay. However, when my tail is right behind my head, then I'm full. But to do so, I need to sacrifice this empty space. If I don't sacrifice this empty space and I put something here, then when I move my tail forward after putting something here, the tail is equal to head, and then I will think it's empty. Actually, it's full. Okay. So how can I solve this problem without sacrificing this empty space? Well, because here I can only put 4, and I created it with capacity 5. I was hoping to put 5. So now, whenever I create something, I have to create it with capacity plus 1. Yeah. So the solution is actually quite simple. How to solve this is I have to remember each time I put something in the queue, each time I NQ, I will remember how many are there. So I have to count. Each time I put something, I add one, add one, add one. Oh, I DQ, remove one, and so forth. And each time I have to check, is it empty, I look at the count. If the count is 0, it means there's nothing there. But how do I know it's full? Well, I have the capacity. If the count is equal to the capacity, then I'm full. Yeah, it's easy. So I'm not sacrificing an empty spot here. But I still need to know where the head is and where the tail is. So here's the solution. Okay, I will have a tail that points to the next position where I will add something, and the head is the position for the next one to be served. And I will have a count that I will cache, where I will count the elements that I have. Okay. Now each time I DQ, I have to remove from the head and increment the head, move the head, but because I DQ'd, I have to remove also from the count. And each time I NQ, I add to the tail, I move the tail, I increment it, but I also add an element in the count. So the count is always consistent with the real state, how many elements I have here. Okay. So now that we understand the behavior that we would like to have with this new abstract data type, let's sign a contract. Define all the methods that I want to have. This is what I want to have. The creator of this class, we'll call it CQ, I want to give it the capacity, and it will create a queue that has that maximum capacity. Then I want to be able to unqueue an item. I want to be able to dequeue, so remove an item. I'd like to peek, check at the head who's in there. I want to check if the queue is empty. If the circular queue is full, I want to ask the size of the circular queue. I want to remember the capacity. Hey, give me the capacity, and I'd like to reset it. Actually, notice that this interface is exactly the same as the interface that I had for the bounded queue. The only difference is that the creator is different because the class is different. Okay, the other one was bounded queue, this one is a circular queue. But the way I talk to it is exactly the same. So let's implement it like we did with the bounded queue. We will also raise exceptions when we have issues. And okay, let's see how we'll do it. So first thing is the constructor. Okay, here's my class, circular queue or CQ, whatever we're going to call it. And my constructor is this init. I will give it the capacity along with self. And the first thing I have to do is make sure that what is given to me is correct. So here's another way of doing the test. I could have also using assert or whatever. But here I'm checking if the type of capacity that is given to me here, if it's not an int, or it is an int, but the capacity is negative or equal to 0, then I raise an exception. How do I raise an exception? I raise an instance of the class exception to which I give the argument capacity error. Why is 0 here? Well, because creating a queue of size 0 makes no sense. Okay, why would I create a queue of size 0? I can't put anything in there. And negative, same thing. It's irrelevant. And obviously, if it's not an int, it's a problem. Okay. Now, if this test is fine and I'm not raising an exception, well, I will initialize all my properties. What are my properties? I need a list to store my items, and here's my list. In the beginning it's empty. I need a capacity. Remember the capacity. The capacity is given to me here, so I just assign it to capacity. I need a count to know how many elements I have in my queue, and in the beginning is 0, I have nothing. And then I have a tail and the head that tell me where in this list the head is and where's the tail, and in the beginning there's nothing, so they are 0. Okay, so here's my object that I'm creating. The public sees from outside just the methods that I can have. The properties, these are private, so I use the underscore here as a prefix for the names of these properties to indicate, this is a convention, to indicate that these are private, shouldn't be touched from outside the class. Okay, so that's the creator. Notice that here I initialize my items as an empty list. There's nothing in there. Okay, I could have done it differently. There's another alternative, and I'll talk about it soon. So now that I have the init, what do I have to do? I look in my methods here. Well, let's see the enqueue. How do I add an element in my queue? Enqueue. Well, I provide the item to add in the queue. And the first thing I have to check, well, can I add this item in the queue? Well, it depends. If it's full, there's no room. So how do I test whether the queue is full or not? Remember, I have the count. The count here tells me how many elements are in my queue. So I check. If the count is equal to capacity, well, I use all the space. So it is full. I raise an exception, say there's an error. Queue is full. If this condition is not true, that means everything is fine. Actually, there is room, and therefore I need to add the item in the queue. Well, there are two cases. If the length of this list where I put the items is still smaller than the capacity, it means that there's no time where actually I reached the capacity. So I had less enqueuing than the capacity itself. In that case, it means that the queue has the list hasn't growing to that point. And because it hasn't grown to that point, if I'm adding something, I just append it. Okay? And this is why I have, in the case of the length being of items is smaller than the capacity, I will just append this item to items. Otherwise, well, it means I have all these spaces already. I have capacity spaces. Then to add this item, and I have room for it because I didn't reach capacity, the count hasn't reached capacity. It's not at this time anyways. Then I'll take that item and I'll put it in the position tail of items. Okay, so in both cases, my item has been added to the items, and therefore I have to increase the count. I have a newcomer in this queue. I increase the count, and also I have to move the tail to the left. How do I move it to the left? I increase by 1. But I have to be careful not to go beyond the boundaries, so I do modulo capacity. Okay, so if you trace it, how this works, imagine I have a queue that I create here of capacity 4. So in the beginning it is completely empty. The list that I created for it is completely empty. When I enqueue 45, yeah, I have room, so I come here. Oh, the length is 0, and 0 is smaller than capacity, smaller than 4. Then I append the item, and that's how I got 45. Then when I enqueue 67, same thing. My size is currently 1. 1 is less than 4, so I will append it. And that's how I got 67 after the 45. Then 23 comes. I have to enqueue 23. Same thing. I have size 2 right now. It's less than 4, so I will append the 23. And this is how I get this. So I'm still at 3. I didn't reach full capacity, and here suddenly I dequeue. When I dequeue an element, it's the 45 that is first to be served, and it'll be removed from the queue, but instead of shifting everything to the right, no, I actually will erase it, override it with a none. Okay? Now, where is my queue? My queue starts here at 67 and then 23. I have two elements in there. The count is 2. If I NQ 18, well, I come here and say, hey, what is the length of items? I have 3. 1, 2, 3. So it's smaller than 4, and therefore I will append 18. And that's why I got none, 67, 23, 18. My queue is actually 67, 23, 18. When I dequeue, I take the first to be served. It's 67. 67 is gone and replaced by none. Okay. Now, if I NQ 39, where will 39 go? It doesn't go after 18. Why? Because I have 1, 2, 3, 4 elements in my list of items. So when I come here, 4 is not smaller than 4, and therefore I will go to the else. And here I will put the item 39 into the position where the tail is, and the tail is in the beginning here, the first available space. So I'll get 39, non-23. So you see already the effect of this circular queue. But the instance circular queue looks like this. Materialized, it's basically the list of these, the collection of these properties. The items is a reference to a list that has 39, non-23, and 18. Look what I have here. The capacity is still 4. The count tells me 3. Indeed, I have 1, 2, 3. 3 elements. Where's the head? A 2. Yeah, 0, 1, 2. That's the head. That's the first to be served. And tail is telling me where's the first place where to put something. And 0, 1. And indeed, it's here, 0, 1. So that's the tail. Okay. So basically what happens is that in the beginning here, this is growing to the point where I reach capacity, and at one point then it's the head and tail that will tell me where the data is. Okay, so this can change if we have a different alternative. The different alternative is basically I would not have to do an append if when I created my queue, my circular queue, I already filled it up to capacity with nones. Okay, I would get, so for example, I create a circular queue of 4. Instead of creating completely empty, I created with 4 nones. None means nothing. In other languages, they say nil or null, or in Python, they say none, means there's nothing there. Okay, but the space is there, but there's nothing in that space. Now, here's another alternative. Had I created my instance this way, so in the beginning I check if the capacity is correct, and if not, I raise an exception. If I don't raise an exception, when I create my items, I say create as many nones as the capacity. Okay, so then I have a list as big as capacity. It's ready. It doesn't have to grow anymore. It's ready. So I don't need to append. I go directly to the position, and you can see in the NQ, I don't have an append, and I don't have a condition, do I append or not. I immediately go to the tail of self. At that position in items, I will add the item. Okay. So we have two alternatives. Which one is better? Actually, they're the same. It's just a preference of style of how to write this. But in terms of time and efficiency, it's exactly the same. Now dequeuing. How do I dequeue? Well, to dequeue, I first have to make sure that I have something to dequeue. So how do I check? I don't want it to be empty. How do I know it's empty? Well, if the count tells me you have 0 elements, it means it's empty. And then I raise an exception. Sorry, queue is empty. If it's not empty, then I can dequeue something. Where do I dequeue it? At the head. So I go to the head of self, and there should be a dot here. Self in items of self, and I store it here in my local variable item. Once I have it, then I can go to that spot, head of self, of items, and I'll put a none there. I erase it. Boom. It's okay. It's not a problem. I put a none there. I stored it already in this local variable item. Then immediately after, I will remove 1 from count because I remove somebody, and count is telling me how many are in there. And then I move my head forward, modulo the capacity, so I can go around. Now that I'm done all this work, that item that I stored here, I return it. Done. That's the DQ. And I change the state of my queue because I have one element less, and that's why the count is one less, and my head is pointing somewhere else, the next one that will be served next time. Okay, but peak will not change the queue. The state of the queue will not change. And you can see, how do I peak? Well, I peak only when I have an item in the queue. If the queue is empty, you say, whoa, whoa, exception here, queue is empty. Again, so I check if the count of self is 0, then I raise an exception and say the queue is empty. Otherwise, I will look at who's at the head of items, and that's what I return. I did not take it out. I did not overwrite with none. Leave it there. I just return a copy of it. Okay, and that's how I peak. Now I need to check, is it empty? Is it full? How do I check is it empty or full? Well, I check count. So is empty, I'll ask, is count equal to 0? Then I return true. If count is not equal to 0, I return false. No, it's not empty. There's something there. Count tells me there's something there. How do I know it's full? Well, I ask count. Hey, is count equal to capacity? If count is equal to capacity, then I filled my queue and I have to return true. If not, return false. Easy. Now, what about the size? If I want the size, well, I'm counting it. So again, I will return the count. I ask the count, hey, how many are there? Boom, I return that. That's the size. Capacity, I'll ask capacity because I stored it. I cached it. Hey, capacity, return that. Okay. What do we still have? We have clear, which resets the queue. And then we have a way to transform a queue into a string, for example, so that I can print it. So let's start with the reset, which is clear, function clear. So clear is simple. I put back the items at an empty list, or I reassign it to as many nones as capacity. So you remember alternative 1 or alternative 2. And then I put the count at 0 because it's a new queue. The head is at 0 and the tail is 0. So the reset is very simple. Now for string is a function that is either called explicitly, and I call it with str. I ask an object, hey, make yourself into a string. Or I call it implicitly. For example, if I have a variable and I print it, print will call str because print only prints strings. Okay, so I need to define it in order to be able to call it later, either implicitly or explicitly. So what is string doing? String is basically taking this instance of the class Q, circular Q, and make it into something that is string, so it will return a string. Let's build the string. So to build the string, we'll decide to have a closing square bracket and then all the elements in my queue and then a closing square bracket just to show that it's actually queue going in one direction. It's just a choice we have. So we will start a string expression with that closing square bracket. And then I have to put all the elements in the queue, one after the other, concatenate them in that string, and then close it. But where are the elements in that string, in that queue? Well, the elements in that queue start from the head. So I will have an index I from the head, starting from the head, and then I will traverse all the elements in my queue. How many are there? Well, count will tell me. So in the range of count, I will traverse what? I will go one by one, starting from this head at position I, and I will take that element at position I of items, transform it into a string, append it or concatenate it to the string expression, put a space after it, and then go to the next one. How do I go to the next one? Well, I have to increment I. How do I increment I? I is equal to I plus 1. But because it's circular, I do modulo capacity. to allow it to go around. Once I finished grabbing as many items in items as count, then I close my string expression with this square bracket, a closing square bracket, and I return that. And that's how I get my string. So for example, I could get something like this. Okay, so the square bracket, the elements, I have here 5 of them, and then I close the bracket. Okay, and you see you have a space after each one of them, even the last one. Okay. Now, in addition to string, which, as I said, transforms an instance of that class into a string, there is another method that transforms also an instance of a class into a string, but with additional information if necessary. We call it a formal representation of the instance as a string. The string is informal. The repr representation is a formal representation of a string. And in this particular case, what is the information that is missing, for example, here? I don't know where these elements are positioned in the real list. Where are the nones? I don't see them there. There's no information about where's the head, where's the tail. Well, I know that this is the head, the 2 and the 6, but what is the index of the 2? What is the index of the 6? I don't know. What is the capacity here? I don't know. So I'd like to display that and have it in the official representation of an instance circular queue. And therefore, what I'll do, I will create also a string with repr. I will start with the string conversion of the items, which is a list. I'll convert it into a string, but I'll also concatenate to it an h equal to the head. I will transform it into a string. That's a string method of the class integer. This is the string method of the class list. Okay, but it's not the same function here. It's a function of 2 different classes. And then I concatenate t equals the string representation of the tail plus parentheses plus, these are concatenations, the conversion of a count into a string, slash conversion of the capacity into a string. And then I close the parentheses. So that same list that you see here would have this repr representation. You can see I have a none, and then 2, 3, 4, 5, 6, and then a none. You wouldn't have known that here, but with the repr you do. And then I can see the h, well, the head is at 2. Oh yeah, 0, 1, 2, indeed, the head is here. And the tail is at position 7, 0, 1, 2, 3, 4, 5, 6, 7. Yeah, that's where I will put the next one. Okay, and I have 5 elements out of 8. My capacity is 8. Okay, so I have all the information with repr. Now, if I dequeue something and then unqueue 8, then I check the representation and I'll see it changed. And this will allow me actually to trace and debug my data structures, for example. Okay, so the difference between string and repr, both will take an object and make their representation into a kind of a string, but str is more an informal kind of string representation of an instance of the class, while repr is more an official or formal representation of an instance. How do you call them? The str is called by str like this. You don't put the underscore except when you define the function, but when you call the function, it's just an str, or can be called implicitly inside a print statement. The repr, same thing, you have the underscore, repr, underscore when you define it, but when you call it explicitly with repr and the parentheses. So let's see an example. Here I have some code, and I will try the circular queue. So I start assigning a circular queue of 4 to q, and then an unqueue a, I add a, and then let's print the repr of q. Well, this is what I will see. This is an alternative one where I created an instance of a list. So the list is representing the queue, the circular queue, but the list is flat. I didn't put anything in it. Then I basically appended the A, and you can see the head is at position 0, the tail is at position 1. The next one, where I will add something, and I have one element out of 4. So I have a queue indeed of size capacity 4. The second alternative, had I initialized this list with none, 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 then I will see A, none, 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 and H as 0 and T at 1. Same thing as here, except that here I initialize it with nones. Now I NQB, I NQC, and I check the repr. This is what I will see. A, B, C in this case. I appended them, while in the second alternative I will see A, B, C, and none. Same thing with the head and tail, and you can see I have 3 out of 4. Now I NQD, and then check the repr. Here you can see I have A, B, C, D, and here I have A, B, C, D. So they actually, both alternatives now, they are the same. Okay, and you can see I have a head at position 0. That's the first one to be served. The tail is also at position 0 because I reached this point, and there's a modulo the capacity, and I ended up here. And same thing here. And I have 4 out of 4, so it's full. Let's try it. If I try to NQE, another one, except if I have an exception as E, I will print the arguments of E. Well, what do you think will happen here? Well, there will be an exception because this is full. And it tells me, error, Q is full. Okay. Now let's DQ an element, and in the first alternative as well as the second alternative, because I reached already the full capacity here, you can see that I DQ'd the first element, which is none. DQ the first element is none, exactly the same thing. So A is gone in both cases. And I have my head now moved at position 1, same thing as here, and my tail is, there you go, this is the place where I will put the next one. So if I DQ now 3 elements, one after the other, it'll be B, C, D gone, and then I'll print the representation of Q. I will get none, 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 and same thing in the second alternative, none, 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 none. So the difference is only in the beginning when I start populating the queue. But afterwards, you see alternative 2 and alternative 1 are exactly the same. If now both of them are empty, so I have an empty circular queue, if I try to DQ from it, except if I have this exception as E, what will happen? Well, print the arguments of E. What do you think will happen? Well, this will raise an exception because I'm trying to DQ from an empty queue, and the exception will be caught here. I have it as E, I will print the argument, and indeed I get error, Q is empty. Okay, so that's the circular queue. Very simple. By the way, consider this in assignment 3. You will have a need for a queue and use the circular queue. So the queue, as I said, you have 2 ends. It's a linear structure. One end you remove things, you DQ things, and one end you NQ, you add things, the back and the front. And that's the convention, you stick to those. If you want to add and remove from the same ending, then it's not a queue anymore. And there's another abstract data type called the double-ended queue, or the deck, or DQ, where you can add and remove from both ends, and then we call them typically in the interface, we call them append and append left. So I append on the right. When I append on the right is a normal append. When I append from the front is an append left. The same thing with the pop. If I pop and I remove from the right, it's called pop. I remove from the left is pop left. When I peek, I typically peek from the right. If I peek from the left, I call it peek left. And I can have also restrictions on the input or the output, so I can only add from one end, but I can remove from both ends, or I can remove from one end but add from both ends. So these are called restricted decks. And this is useful for many applications. The example that I have here is when you have to schedule different jobs, processes running you have a multi-threaded programming, different threads. You put them in a queue, but sometimes you have a process that needs to run before the others. It doesn't want to wait, so you skip the queue. You put it in the you add it from the front rather than adding it from the rear. So you have these possibilities. So the deck basically visually will look like this. You have a queue, okay, from 0 to n, and from one end here, the left, you append left, you pop left, and you peek left. On the other end, you append and peek and pop. Okay. Well, typically, it's not implemented in contiguous spaces in main memory. You have something like this that we call a linked list. We'll get to it. This is our next chapter. So you have to have something that tells you where the head is, and then something that tells you where the tail is. This is where you append and peek and pop. And the head is where you append left, peek left, and pop left. And basically you have elements that are linked to chain somehow. Okay, this is what we call the linked list, and as I said, we will talk about linked lists in the next chapter. But this is hidden. What matters is how you talk to it. So the deck, you talk to it with append an item, append left an item, pop, pop left, peek, peek left, is it empty, size, reset, to convert it into a string, convert it into a representation, formal representation. You can even ask it show, so that it display in a different way. And if it's bounded, because you can have a deck that is infinite or a deck that is bounded. If it's bounded, then you can also ask it, is it full and what is the capacity? Okay, so there you have it. That's the queue and the deck double-ended queue. Next time we meet, it'll be after reading week, and we'll be talking about linked lists, what you see right here. Okay. Thank you for your attention.